It is the most invisible yet essential material of the modern world. From the skyscrapers that pierce the clouds to the smartphones cradled in our palms, glass is everywhere. But creating a perfectly flat, distortion-free sheet of glass was once considered a physical impossibility. For centuries, glass was hand-blown into cylinders and flattened, resulting in ripples and imperfections that blurred the world. Today, we achieve sub-millimeter precision through a process that defies logic, floating molten rock on a bed of liquid metal. This is the story of float glass, a high-stakes engineering marvel where sand is transformed into liquid, and liquid is frozen into a perfect mathematical plane. We are looking at a process that runs 24 hours a day, 7 days a week, for over 15 years without ever stopping. A single hiccup in the thermal gradient or a microscopic impurity in the raw materials can ruin miles of production. To understand how we achieve this level of perfection, we have to start at the molecular level, where raw earth meets the fury of a furnace hotter than a volcanic eruption.
The journey begins with the batch, a precise chemical cocktail of raw minerals. The primary ingredient is silica sand, making up about 72% of the mix, but sand alone has a melting point too high for industrial efficiency. To lower the energy barrier, engineers add soda ash, which acts as a flux to bring the melting point down. However, soda ash makes the glass water soluble, so limestone is introduced as a stabilizer to ensure durability. Finally, cullet, recycled glass, is added to the mix. Cullet is the secret weapon of glass engineering. It melts at a lower temperature than raw sand, significantly reducing the energy required for the furnace and speeding up the reaction. These materials are weighed with extreme precision. Even a tiny deviation in the magnesium or aluminum oxide content could change the refractive index of the final product. Once mixed, this dry powder is ready to face the inferno, where it will undergo a physical metamorphosis from solid grains to a glowing, viscous fluid. The batch enters a furnace the size of a small warehouse. Here, massive natural gas burners blast the mixture at temperatures exceeding 3,000 degrees Fahrenheit. That is hotter than the lava in a shield volcano. The physical transformation is violent. As the minerals melt, they release carbon dioxide, creating millions of tiny bubbles that must be removed. This stage is called refining. Through a process of homogenization, the molten glass is stirred by its own thermal currents, ensuring that there are no stones or unmelted grains left behind. The heat is so intense that the furnace walls, made of specialized refractory bricks, slowly dissolve over a decade of use. Engineers must monitor the temperature within a fraction of a degree because the viscosity of the glass depends entirely on its thermal state. If it is too hot, it runs like water. Too cool, and it becomes too thick to flow. Once the liquid glass is purified and bubbles are purged, it is ready for the most critical step in its life, the transition into the float bath. This is the heart of the invention, the float bath. Imagine a long, sealed chamber filled with a shallow pool of molten tin. Why tin? Because tin has a high density and remains liquid at the temperatures where glass solidifies. The molten glass flows onto the surface of the tin like oil on water. Because the glass is less dense, it floats, and because the surface of a liquid is perfectly flat due to gravity, the glass takes on that perfect flatness. There are no rollers, no molds, and no mechanical contact on the bottom surface, only the frictionless support of liquid metal. This environment is extremely hostile. To prevent the tin from oxidizing and ruining the glass, the chamber is filled with a protective atmosphere of nitrogen and hydrogen. The glass spans the width of the bath, forming a continuous ribbon. This is where the equilibrium thickness comes into play. Left to its own devices, glass on tin naturally wants to be about 6 millimeters thick. To make it thinner or thicker, engineers must use mechanized top rollers to stretch or compress the ribbon. As the glass ribbon leaves the tin bath at about 1100 degrees Fahrenheit, it is solid but still highly stressed. If it cooled too quickly, the internal tension would cause it to shatter into 1,000,000 pieces. To prevent this, the ribbon enters the leer, a massive annealing kiln several hundred feet long. In the leer, the glass is cooled with extreme precision along a specific temperature curve. This allows the atoms in the glass to rearrange themselves and relieve internal stresses. Think of it like a controlled cool-down after an intense workout. We are tempering the molecular structure to ensure the glass is strong and easy to cut later. Sensors track the temperature at every inch. If one side of the ribbon cools faster than the other, the glass will warp. By the time it exits the leer, the glass is cool enough to touch and as transparent as the air itself. It has traveled hundreds of feet, transformed from red-hot liquid to a rigid, crystal-clear sheet, ready for the final transformation. The continuous ribbon of glass now reaches the cold end of the production line.
Here, high-resolution cameras and laser scanners inspect every square millimeter. They are looking for seeds, tiny bubbles, or stones, which are microscopic bits of refractory brick. If a defect is found, a computer tracks its exact location. Next, the glass must be cut into manageable sheets. This isn't done with a saw, but through scoring and snapping. Diamond-tipped wheels or high-power lasers create a microscopic fracture line on the surface. Precisely timed mechanical snappers then apply pressure, causing the glass to break cleanly along the scored line. The edges are often jagged and sharp, so they pass through a series of grinding wheels that smooth the perimeter to a pencil edge or bevel. For specialty glass, like that used in high-performance electronics, the precision is measured in microns. This is the final stage for clear glass, but for the world of mirrors, a secret chemical process is about to begin. To turn a piece of transparent float glass into a mirror, we must apply a reflective coating. This isn't just silver paint, it is a series of delicate chemical reactions. First, the glass is scrubbed with cerium oxide and demineralized water until it is perfectly clean. Then, a sensitizer, like tin chloride, is applied. This prepares the surface to bond with the metal. Now comes the magic. A solution of silver nitrate is sprayed onto the glass. Through a chemical reduction reaction, the silver atoms precipitate out of the liquid and bond to the glass surface, creating a layer only a few atoms thick. To protect this precious silver from oxidation, which would turn it black over time, a layer of copper is often deposited over it, followed by multiple coats of moisture-resistant paint. The result is a surface so smooth that it reflects light with nearly 95% efficiency. You are no longer looking at glass. You are looking at a high-performance optical instrument built from sand, tin, and silver. Before any glass leaves the factory, it must prove its metal. Quality control is a brutal process. Samples are taken from the line and subjected to impact tests, where heavy steel balls are dropped from heights to ensure the glass doesn't shatter into dangerous shards. We check the optical distortion by projecting a grid through the glass. If the lines bend even a fraction of a millimeter, the sheet is rejected and sent back to the furnace as cullet. For mirrors, we use salt spray tests, simulating years of exposure to bathroom humidity and cleaning chemicals to ensure the silver backing doesn't peel. We test thermal shock by moving glass from freezing to boiling temperatures in seconds. Only the most perfect sheets survive. Engineering glass is about more than just clarity. It's about the reliability of a material that we trust to hold back the wind at 60 miles per hour on a highway, or to keep the heat in during a sub-zero winter. From a pool of liquid tin to a flawless reflection, the journey of glass is a testament to human precision. I hope this deep dive gave you a new perspective on the strategies and the relentless mindset behind these global icons. If you enjoy deconstructing business empires and tech legends in this tech archive style, make sure to hit that subscribe button and turn on all notifications. That way, you will never miss a new blueprint of history. For those of you ready to explore more boardroom coups and technological breakthroughs, I have handpicked 2 videos for you right here on the screen. Click one to keep watching. I will see you in the next one. Thanks for watching.